differentiation undoes integration, and integration undoes differentiation up to a constant. So, just to remind you what this means, you have some function, and I mean, if we want to be really formally correct about it, this needs to be an integrable function. Sorry, an integrable. What that word integrable means, we're not going to actually look at until very near the end of the course. But any continuous function on a closed interval, such as, so what's a closed interval? A closed interval means that we're including all of the points between 2 points A and B on the number line, and we include the endpoints. So this set is often denoted by square brackets A comma B. Hands up if you've seen this notation before. Yeah, good. Okay. So suppose we have a continuous, you guys forget about this word integrable for the purposes of what I'm talking about today, just think of it as a continuous function defined from A to B and at all points in between. So what integration means, and in some sense, I mean, we can be very rigorous about the definition, which we will do later on, but what integration means is finding that area. And that's actually a really thorny question, right? Because we know how to calculate areas of squares. That's easy. We know how to we know how to calculate areas of triangles. That's easy. But once I start putting squiggly lines, the question of what the area actually means becomes conceptually, an extra leap. So I would encourage you to actually reflect on the fact that you're making an underlying assumption that area actually means something at all. And whether or not we can calculate that area and whether we can attribute a good meaning to that area is something that we'll discuss a lot later on. But just keep that in mind. You're already making an assumption the minute that you say, I'm going to define something to be the area of that shape. You're assuming that area has a defined meaning. So let's just suppose that that's the area, and this area is denoted by the integral. So this is the function f of x. This is the x-axis, this is the f of x-axis. The area is denoted the integral from a to b of f, or more commonly you will have seen it as integral from a to b of f of x dx. Okay? So that's our notion of what, for the purposes of this lecture at least, and for most of the course, that's our notion of what integration means. It means calculating that area. And what this differentiation undoes integration really means is that if I define a function, a new function, I'm going to define capital F of x to be the integral from a to x of f. And this is where the fact that I'm not writing of x dx sort of is important, because what the variable that we put in this, you guys have heard the term dummy variable, yeah? Is that something that's still used? No, okay. So this symbol x that's used in the brackets in this dx, what that symbol is almost totally irrelevant. The only important thing is that symbol is not used anywhere else in the symbol for the integral. So if I want to do it here, I'm going to actually have to make the variable t, because I've already used x. But what am I saying here? What I'm really saying is I'm defining a new function where this x value is a variable, and this area here is capital F of x. Okay? So I define a new function to be the area under this graph where this x-coordinate changes, and that's the changing variable in my function. Okay? And fundamental theorem of calculus says that if I take the derivative of this, I get the value of the function here. So that's the value f of x there.